Hello there, and welcome back to the Sleep Science. Tonight, you're not falling asleep to bedtime stories of rainy forests or softly creaking pirate ships. No, tonight, you're drifting into something far older, far stranger, and far, far larger, the quiet before the universe. Picture it not a black void or an infinite field of stars, but actual nothingness. No light, no space, no time, not even the concept of before. Just a deep, breathless stillness that doesn't even know it's still. And somehow, this is where it all begins. You probably won't survive this story, not in the physical sense, but in the your concept of existence is about to be tenderly scrambled kind of way. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, let me know where you're listening from and what time it is. I love seeing just how far these sleepy stories travel. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You drift through non-being, and even the word you feels like a cosmic overstatement. No up, no down, no here. And yet there's something, a tension. Not exactly a sound, more like the potential for sound. Like the silence before a storm if the storm were the birth of literally everything. This isn't just empty, it's unstable emptiness. A vacuum with attitude. Physicists call this a quantum vacuum, but don't let the word vacuum fool you into imagining cleanliness or sterility. This vacuum is more like the jittery backstage of existence, where energy fizzes and twitches even though nothing is supposed to be happening. Virtual particles blink in and out of being faster than you can say Planck time. These fluctuations, tiny, random, and absurdly energetic, might be the reason we're all here. Here's the fringe bit. Some cosmologists argue that our universe wasn't even a unique event. That maybe, just maybe, universes are constantly bubbling into existence from this quantum foam like champagne fizzing in a bottle you forgot you shook. Multiverse theories abound, though historians of science still argue whether the ancient idea of an eternal, cyclical cosmos anticipated these modern ideas or just stumbled across them by metaphor. But back to your drifting. You hover in this paradoxical void where nothing and everything blend in awkward silence. It's not the kind of darkness you'd find at night, where there's still air and heat and the occasional cricket. No, this is perfect nothingness, except, well, something about to give. And when it does, it's not a bang. There's no pop or scream or celestial fireworks show. Instead, there's expansion, instantaneous, exponential, and wholly unreasonable. You're not watching the universe get bigger, you're watching it become. In less than a fraction of a second, the quantum jitters of nothing inflate into something the size of a grapefruit, and then, boom, galaxies worth of space. This phase, charmingly called cosmic inflation, isn't polite. It's wild. It expands faster than the speed of light, which, by the way, is totally allowed here because space itself is what's doing the moving. The speed limit only applies to things in space, not to space itself. Meanwhile, everything's absurdly hot. Like, atoms can't exist yet hot. You wouldn't survive a millisecond, not even as atoms, because atoms haven't formed yet. But you aren't made of anything right now, so that's fine. You're weightless in a storm of pure energy. Quarks dart around like toddlers on espresso, occasionally teaming up with gluons to form the first protons and neutrons. But they won't get very far. Electrons are still out there somewhere, lurking and waiting to play their part. Somewhere in this subatomic soup, the laws of physics are settling in like house rules at a very intense dinner party. Gravity shows up first, demanding attention. Then come the strong nuclear force, the weak nuclear force, and electromagnetism. For a brief moment, they might have all been one unified force, a kind of physics Voltron. But now, they each go their own way, doing their specific little dances. Historians of science often muse whether ancient alchemists, obsessed with unity and elemental forces, were unknowingly grasping at this grand unification. And time, oh yes, time has started ticking. Slowly at first, or maybe fast, it's hard to tell without a reference point. But once energy exists, entropy comes along for the ride. That's the universe's way of keeping time, a gradual, irresistible slide from order to chaos. This is the great irony of it all. From absolute stillness and symmetry springs motion and asymmetry. The tiny imbalance between matter and antimatter. About one extra particle of matter for every billion antimatter ones is the whole reason anything remains. The rest just annihilated itself in one glorious, blazing hug of mutual destruction. Fringe alert again. Some physicists speculate that this imbalance may be tied to mysterious fields we don't fully understand yet, like the hypothetical, inflattened field that may have driven the early expansion. It's kind of like blamming a fire on a dragon you're pretty sure exists but have never quite seen yet. And you, lucky traveler, are now sailing through the cosmic aftermath of creation. You're a ghost in the machine of time, watching the rules take root, the forces stretch their legs, and the universe stumble into its awkward infancy. No stars yet, no galaxies, no light really, just an opaque, seething plasma, so hot that photons can't travel more than a millimeter before slamming into a free electron and getting rudely bounced back. It's like trying to see through a fog machine filled with lava. The cosmos is technically glowing, but the glow's trapped inside, muffled by the density of matter. Eventually, things will cool down. But for now, you hang in this bizarre, dazzling prelude, where the most important thing happening is waiting. Because soon, very soon, the universe will cool just enough for light to break free, and then you'll see the real magic begin. The waiting pays off. You float through time, gliding just a little closer to the moment when light is finally allowed to stretch its legs. The universe has calmed down slightly. It's still hotter than any furnace ever built, still denser than anything you'd care to be caught in, but it's slowing, expanding, cooling. The primal chaos is simmering into something almost manageable. And then, like the first sigh after holding your breath too long, it happens. Photons are finally freed. This moment, roughly 380,000 years after the Big Bang, is called recombination. That's when electrons and protons finally settle into proper relationships, forming hydrogen atoms like overachieving blind dates who just clicked. Once those electrons are locked into orbit, photons stop getting scattered every few nanometers. For the first time, light travels freely through space. And you, lucky little wisp of cosmic curiosity, get to witness what's called the cosmic microwave background. Not a beam, not a burst, but a bath, gentle, omnipresent, still echoing across the universe today. You can even tune into a bit of it on old analog TVs, about 1% of that static between channels. That's the universe whispering its baby pictures into your living room. And here's your mainstream historical anchor. In 1965, scientists Arno Penzias and Robert Wilson stumbled across this background radiation while trying to clean up some inexplicable noise in a radio antenna. They thought it was pigeon poop. Turned out, it was the afterglow of creation. Nice save. Now imagine the universe as a warm, glowing mist, stretching and cooling, its energy diffusing like steam escaping from a kettle. But it's more than just a pretty glow. This light holds fingerprints, tiny ripples, temperature fluctuations, density differences, all seeds of future structure. Galaxies, stars, planets, pretentious coffee shops, they all owe their existence to the unevenness of this ancient light. If the early universe had been perfectly smooth, we wouldn't be here. Symmetry might be beautiful, but in cosmology, it's terribly unproductive. Fringe fact time. Some scientists believe that those initial fluctuations may be quantum in origin, tiny jitters from the inflation period, stretched to cosmic scales. Which means that everything, the walls of your room, the freckles on your shoulder, the regrettable text you sent last night, might trace back to subatomic noise amplified by a universe in overdrive. You drift farther, deeper, slower, and everything is redshifting now. Space is expanding, which means light traveling through it gets stretched, its wavelength growing longer. Energetic blue shifts into calming red. Over billions of years, that once blazing glow has mellowed into the microwave range, harmless, ancient, and everywhere. Here, where the universe starts showing its work. Hydrogen dominates, by far the most abundant element. It's lonely, simple, elegant in its minimalism, just one proton, one electron. Helium's tagging along too, created during the first 3 minutes of nucleosynthesis. But that's it for now. No carbon, no oxygen, definitely no iron for swords or coffee grinders. Just a sea of hydrogen and helium and the creeping whisper of gravity saying, "Hey, come closer." But before gravity gets its way, there's one more thing to savor: silence. The universe is still eerily quiet. There's no sound because sound needs a medium, a gas, a liquid, something to wiggle through. And while the early universe was a hot plasma, it's now so diffuse and thin that no meaningful vibration passes through it. Everything is moving, stretching, cooling, but silently. It's unsettling, like watching a fire from across a vacuum. Of course, that won't last. The silence is temporary, because gravity is patient and gravity is greedy. You notice subtle differences. Some pockets of matter are a little denser than others. These are the wrinkles in spacetime you saw earlier in the cosmic microwave background, and over millions of years they begin to tug. Denser regions pull in nearby gas. Gas condenses. Gravity gets bolder. This is the start of structure formation. The blueprint, been there all along. It just took the universe a few 100 million years to cool down enough for the plan to kick in. You zoom in on one of these growing knots of gas, a dark patch among dark patches, barely distinguishable from its neighbors, but it's pulling, warping, heating. Matter is falling inward, spinning, colliding. You can't quite see anything yet. There are no stars to shine light. These are the dark ages of the universe, not metaphorically, literally. No light sources, just gravitational sculpting in the shadows. Historians still debate whether ancient mythologies of chaos and void unknowingly reflect some intuitive grasp of this pre-stellar epoch. Maybe. Or maybe humans just instinctively fear the dark. But hang in there, the first stars are coming. You can feel it, can't you? That building tension. The clouds are thickening, collapsing under their own weight, and in their hearts pressure is rising. Temperature climbs. Hydrogen atoms slam into each other with such violence that their electrons are ripped away and their protons fuse. When that happens, energy escapes, and just like that, the lights turn on. These first stars are monsters. Massive, short-lived, dramatic. They burn hot, live fast, and explode spectacularly. But we'll visit those in a bit. For now, enjoy the unfolding. Back at the larger scale, the universe is starting to look a little more familiar, well, vaguely. Gravity doesn't work randomly. It favors structure, sheets, filaments, clusters. Matter flows into these patterns, forming a vast web, what cosmologists call the large-scale structure of the universe. Think spiderwebs, but cosmic. Galaxies will eventually form along these strands like beads on a string. And you float among them, watching a pattern emerge from chaos. The rules are in place. The tools are simple: gravity, expansion, and a bit of leftover energy. Yet from these, an entire universe unfolds. And it's still unfolding. You coast along the newly brightened corridors of space, and it's breathtaking. Well, it would be if you had lungs. The first stars, those ancient, ferocious giants, are lighting up the darkness like a fireworks finale you didn't know the cosmos was capable of. They're not like the stars you're used to, though. These are population III stars, and they are the drama queens of the stellar world. They form from pure hydrogen and helium. No metals, no clutter, nothing that can cool the gas clouds down quickly. As a result, they grow huge. Dozens, sometimes hundreds of times more massive than our sun. And like any creature that burns too hot too fast, they live short, tempestuous lives, just a few million years before they self-destruct in spectacular fashion. From your place among the stars, you watch them spark to life and die in quick, furious succession. It's not just entertainment, it's alchemy, because when these stars explode, they forge the elements the universe needs to get creative. Carbon, oxygen, nitrogen, iron, gold, the good stuff. These ingredients aren't made in neat little labs, they're born in collapse, in fire, and the death throes of giants. Every breath you'll ever take, every bite you've ever chewed, every annoying sibling you've tolerated, all made of atoms spat out by stars that blinked out billions of years ago. Carl Sagan said we are made of star stuff. He wasn't being poetic, he was being terrifyingly literal. Mainstream science has a favorite poster child for this process: the supernova. A star runs out of fuel, loses the pressure to keep itself inflated, and collapses under its own weight. What follows is a detonation so intense it briefly outshines an entire galaxy. And in that moment, boom, heavier elements are born. It's like a cosmic piñata if instead of candy, it rained periodic table entries. Fringe alert. There are some alternate hypotheses that challenge the idea of a clean start with just hydrogen and helium. Some fringe physicists propose that trace amounts of heavier elements may have existed from the very beginning, leftovers from a previous universe maybe. A kind of atomic inheritance. It's speculative, but it's fun to imagine the Big Bang as not the beginning, but merely the latest chapter in a very messy cosmic family saga. Either way, you're now traveling through a universe that's getting more interesting by the minute. Not just light, but complexity. Gas clouds enriched with metals, more stable conditions, the formation of binary stars, then stellar clusters, then galaxies, real ones, massive, swirling collections of stars and dust and dark matter, all held together by gravity's stubborn fingers. And those galaxies, they're everywhere, spiral, elliptical, irregular, cosmic snowflakes, each with their own temperaments. You glide past a spiral just forming, arms extending outward like a dancer twirling in slow motion. Gravity, again, is the choreographer. It's the same force that dropped your phone last Tuesday, and it's shaping the heavens with casual elegance. Within these galaxies, stars begin forming in generations. The first big drama queens are gone, but they've left behind the materials for quieter, more stable stars like our sun. You'll meet it later, but for now, just note that not all stars are built to implode. Some prefer a long, steady burn. Good for life, good for storytelling, bad for dramatic exits. As you float farther, you begin to feel the scale of it all. This isn't just big, it's impossibly big. Millions of galaxies, trillions of stars, each one a potential host for planets. Each planet a stage for some version of physics to try weird little experiments. You, drifting now with the ancient light and supernova dust, start to understand. This isn't just the universe becoming visible, it's the universe becoming a story. Historians of astronomy often trace the first human musings on the stars to Babylonian records etched in clay tablets, circa 1200 BCE. They tracked planetary movements with impressive precision. But you wonder, what would they have thought if they could see this, the first stars being born, long before Earth existed? Probably something between worship and sheer panic. By now, you've watched the first few billion years pass like a fast-forward reel of cosmic adolescence, and galaxies are no longer isolated. They're forming into groups, clusters, even superclusters. They're bound not just by gravity, but by invisible tendrils of something strange, dark matter. You can't see dark matter, but you can feel its influence. Galaxies spin faster than their visible mass should allow. Something is holding them together. A hidden mass that doesn't emit or absorb light but exerts gravitational pull. Scientists know it's there. They've mapped it indirectly, but what it is, that's still up for grabs. WIMPs, axions, primordial black holes, take your pick. Historians still argue whether dark matter will be identified in the next century, or whether it's the physics equivalent of searching for Bigfoot in a particle collider. Still, it's part of the story. An unseen hand shaping the universe, laying the groundwork for everything to come. And speaking of groundwork, you're about to pass through a swirling nursery of gas and dust. Something's forming. Not a star this time, but something smaller, denser, more complicated. The building blocks of a solar system. But before we get there, you take one last look at the night sky, now teeming with light. Not the artificial glow of street lamps or phone screens, but real light, ancient, unfiltered, impossibly vast. You think about those first photons, still zipping through space, carrying with them the story of everything. And somewhere, tucked into one of these newly formed galaxies, a quiet little star is beginning to shine. You follow that quiet little star like a dust mote in a sunbeam drifting closer through a slowly swirling spiral arm. This region, our galactic neighborhood, isn't particularly flashy. It's not the bright center of the Milky Way where stars crowd together like fans at a rock concert. No, this is more like the sleepy suburbs of the galaxy. Peaceful, stable, just what a future home might need. The star you're drifting toward has just ignited. It's not too massive, not too small. A middle child of a star, destined for a respectable 10 billion-year career of hydrogen fusion. And around it, a disk of dust and gas is stretching itself into a flattened swirl, a protoplanetary disk. You watch it spin lazily, like pizza dough in zero gravity. Here's the part where things get messy, in a good way. Tiny particles, grains of silicates, frozen gases, carbon compounds start sticking together. They bump, they cling, they form clumps. At first it's all very chill, dust just gathering more dust. But then the clumps get big enough to attract more dust gravitationally. Now it's less static cling and more competitive accretion. Suddenly, everyone wants to be a planet. You're floating through this early disk, and it's like weaving through a demolition derby of ambition. Protoplanets are forming, colliding, merging. Some win and grow large. Others shatter into debris or spiral into the growing star. And then you see it, one oddly familiar third from the star little orb still forming. Earth, not the blue marble you know and love yet. Right now it's molten, violent, and under constant bombardment. But you can already sense it has potential. Mainstream science estimates that the Earth began to form about 4.5 billion years ago. It started as one of many rocky bodies fighting for a stable orbit, and it almost didn't make it. Somewhere around this time, a Mars-sized object named Theia smashes into Proto-Earth in one of the most cinematic collisions in planetary history. From the debris of that apocalyptic crash, something unexpected forms: the Moon. Now the Moon deserves her own spotlight. Without her, life on Earth might have had a very different and very boring trajectory. Tides, axial stability, that haunting glow in poetry, it all started here, in a violent moment of cosmic billiards. Historians still argue whether Theia was a unique object, or just one of many rogue bodies in the chaotic early solar system. Some even speculate we may have chunks of Theia trapped deep in Earth's mantle, a literal cosmic scar we'll never see directly. Meanwhile, Earth is cooling down slowly. Volcanoes rage, the crust thickens, gases leak out of its molten insides and form a primitive atmosphere, not breathable by any stretch, more like a sauna filled with carbon dioxide, methane, and ammonia. You drift through the haze, trying not to inhale. Lightning cracks across stormy skies. Comets deliver water in frozen packages. Asteroids bring rare metals and the occasional extinction event, but let's not get ahead of ourselves. All this while, the sun is also settling in. Its solar winds blow away the last wisps of excess gas from the protoplanetary disk, putting an end to the planet-forming frenzy. The remaining orbs, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, claim their thrones. Pluto lurks at the edge, blissfully unaware of its future demotion. Now, let's do a little planetary roll call, shall we? Mercury, too hot. Venus, beautiful but utterly uninhabitable. Mars, intriguing but kind of a fixer-upper. Earth, ding ding ding, we have a winner. Earth's position in the solar system isn't just lucky, it's perfect. Not too close, not too far. Just the right amount of sunlight for liquid water. It spins at a pace that prevents one side from frying and the other from freezing. It tilts just enough to create seasons, but not enough to destabilize. It has an iron core to generate a magnetic field. And oh yeah, tectonic plates. Now, plate tectonics doesn't sound sexy, but it's one of the planet's best party tricks. Earth's crust isn't a solid shell, it's broken into massive plates that float atop molten rock. These plates crash, grind, and pull apart. Mountains rise, oceans open, continents drift, and in doing so, nutrients get recycled. Heat escapes from the interior. Habitats are created, then destroyed, then created again. It's chaos with a schedule. Fringe side note: there's a theory called whole Earth decompression dynamics, which suggests Earth might have originally been smaller and more compact, then expanded after shedding a massive early atmosphere. It's not widely accepted, but it's the kind of idea that makes you squint at globes and wonder what's being hidden in all those oceans. As you hover just above this chaotic young Earth, you realize it's still a dangerous place. Meteors still rain down occasionally. The atmosphere is toxic. The land is mostly volcanic wasteland, but in the shadows, something is stirring. Pools of water collect in craters. Minerals dissolve. Molecules bump into one another. Simple ones at first, then more complex. You're not quite at life yet, but you're so close you can practically smell it. And it probably smells like sulfur and wet clay. This is the prelude to biology, what some scientists call prebiotic chemistry. Conditions are aligning. Energy, water, and time are doing their slow, quiet work. So you leave the moonlit skis behind and dip low into a tide pool just forming along the edge of a volcanic coastline. Lightning flashes, bubbles rise, something glimmers in the muck. It's not alive, not yet, but it wants to be. You hover just above the surface of that glimmering tide pool, barely a few inches above the muck, and it's hard to believe this gooey chaos will lead to trees, whales, and tax accountants. But that's where physics starts to get playful, because from here on out, it doesn't just build, it schemes. The tide pool hisses under the sun's ultraviolet gaze. Lightning crackles in the distance. Volcanoes belch gases into the thick air. The chemistry down here is anything but casual. Organic molecules are forming, breaking, and recombining in a frantic shuffle, like molecules at a particularly rowdy singles mixer. This, dear sleeper, is abiogenesis, life from non-life. It's not magic, it's physics cranking up the complexity dial. Mainstream science proposes a few candidate locations for life's debut. Warm little ponds, hydrothermal vents, deep-sea alkaline chimneys. Right now, you're touring the tide pool edition, but keep your slippers on. We'll explore others soon. Simple organic molecules like amino acids and nucleotides are showing up everywhere now. Not just on Earth, scientists have found them in meteorites, in interstellar gas clouds, even on the tails of comets. It's as if the universe had the recipe for life written in invisible ink, scattered across every surface, just waiting for the right conditions to decode it. Still, there's a chasm between a handful of molecules and something alive, and that's where the fun begins. Imagine one of those early molecules, say, a strand of RNA. It's unstable, fragile, doesn't do much until randomly it folds in a way that helps it replicate. Suddenly, you have feedback, mutation, competition, natural selection's baby teeth. Historians still debate which came first, the RNA world, where genetic material came before everything else, or the metabolism first model, where networks of chemical reactions paved the way. It's the chicken and egg problem, except the egg is a molecule and the chicken is, eventually, a velociraptor. Fringe researchers even toss in ideas like panspermia, the notion that life didn't begin here at all, but hitched a ride on space rocks like a hitchhiker with really good timing. While there's no hard evidence, it does make meteorites feel oddly suspicious. But for now, assume life got rolling right here, in this shimmering soup. You float downward, shrinking with every heartbeat, until the watery surface stretches wide above you and the molecules loom like skyscrapers. At this scale, time flows strangely. A moment to you is hundreds of years to them. You watch chains of molecules link, fold, replicate. Some fail, some succeed. It's a numbers game, and physics loves numbers. Energy flows in, complexity accumulates, and after untold thousands of iterations, something incredible happens. A membrane forms. It's just a lipid bubble at first, greasy molecules spontaneously forming a sphere in water. But inside that sphere, a primitive metabolic network, and maybe even a self-copying molecule. Congratulations! You're witnessing the birth of the first protocell. Not quite life as we know it, but enough to claim its place at the party. These protocells divide. They mutate. Some absorb better nutrients. Others develop crude energy systems. You float between them like a dream drifting through bubbles. It's not intelligent, it's not even aware, but it works. And the moment it works, physics leans in, strokes its metaphorical chin and says, "Ah, let's see where this goes." This part of the story moves slowly. Millions of years pass as single-celled organisms refine their craft. They invent photosynthesis long before plants exist. That's right, the first solar panels were bacterial. These little pioneers capture sunlight and use it to split water, releasing oxygen as a byproduct. And that, as it turns out, is a major plot twist. Because the Earth's early atmosphere, it's allergic to oxygen. When cyanobacteria start pumping it out like a factory with no environmental regulations, most other life forms panic and go extinct. This event is cheerfully called the Great Oxygenation Event, or the oxygen catastrophe if you're feeling dramatic, which we are. Fringe fact: some geologists believe this sudden spike in oxygen could have frozen the entire planet in a snowball Earth phase. You know things are getting serious when microbes cause global ice ages. You drift now through ancient oceans tinged with green, then blue, then slowly turning clear as iron rusts out of the water and settles into the seafloor. Oxygen builds in the atmosphere. The skies begin to turn blue. The planet smells a little less like death. Through all this, stars continue to burn. Galaxies dance. And yet here, in this tiny droplet of space rock orbiting a middling star, physics is writing an entirely new chapter, one that includes memory. Because somewhere in these cells, a molecule called DNA has taken over the genetic library. It's better at copying itself than RNA. It's more stable, more readable, and it's about to become the cosmic filing cabinet for everything you've ever known. Historians love to point out that we humans are roughly 60% genetically identical to bananas. But floating here in the early seas, you realize it's even more extreme. We're 100% related to everything. All life on Earth shares the same basic machinery: DNA, RNA, proteins, ribosomes. A single algorithm written in chemicals. And all of it began here, in the soup. On a warm, rocky planet in a sleepy corner of one galaxy among trillions. The universe wrote the laws, physics inked the pages, chemistry started improvising, and biology is about to bring down the house. You feel it rising, not just life but evolution, adaptation, struggle, triumph. You leave the tide pool behind, drifting into deeper waters where bacteria form mats like woven carpets, bubbling oxygen upward and building entire reefs before coral was cool. And somewhere on some grain of sediment, a cell divides and forgets how to stop. Multicellularity is coming. With it, new shapes, new strengths, new possibilities. You don't sleep yet, you evolve. You spiral downward now into Earth's ancient oceans, a deep alien silence stretching in every direction. The water here isn't just blue. It's thick with life you can't yet see. Layers of plankton drift like slow confetti. Bacteria churn in mats that ripple with the tide. You're still swimming among single-celled organisms, but they've been busy. Because somewhere, somehow, a few of them got together and said, "What if we just teamed up?" Multicellularity didn't happen in a single eureka moment. It happened in whispers, one cell sticking to another, then a few dividing but choosing not to separate, then a sheet, then a blob, and eventually an organism. You coast past the first of these clumps. They're squishy, inefficient, and wildly experimental. Cells specialize. Some handle digestion, others protect. A few are lazy freeloaders. It's a microscopic society, and like any society, it survives because the physics makes it worth the effort. There's power in being big. You can move more, eat more, detect light, avoid being eaten. And once multicellularity hits its stride, the evolutionary snowball rolls fast. Here's a neat mainstream moment. Around 600 million years ago, during what's called the Ediacaran period, Earth sees its first wave of weirdly shaped, softly squishy organisms. Not quite plants, not quite animals, more like quilted mysteries that hug the sea floor and quietly inhale nutrients. You float above them now, these gentle, slug-like life forms named Dickinsonia, Charnia, and Sprigina. They move without mouths, absorb without guts. They are alien in the truest sense, life but not as you know it. Historians still argue whether the Ediacaran biota were evolutionary dead ends or the quiet ancestors of modern animals. Some say they're distant cousins of jellyfish and worms. Others think they were their own weird kingdom, gone before they had time to say hello properly. Still, something is clearly brewing. Oxygen levels are up. The oceans are warmer. Continental shelves are getting cozy with one another. And somewhere in the muck, something sharp flashes. Teeth. No, not quite. But you're at the edge of the Cambrian explosion, and it's about to get weird. Around 541 million years ago, life goes off the deep end. In a geological blink, the oceans fill with creatures that look like an art student's fevered dream. Trilobites with armored shells, worms with jaws, spiny things with googly eyes, segmented bodies, tentacles, gills, claws. You drift through the water and dodge a swimming Apobinia. It's got 5 eyes and a vacuum hose face. Just behind it, a Wiwaxia paddles along, looking like a soft burrito covered in spikes. And over there, Anomalocaris, a meter-long predator with barbed appendages and a circular, toothed mouth that looks like it's constantly surprised. This is evolution when it decides to throw every idea at the wall and see what sticks. The result, the foundations of every major animal group that still exists today: arthropods, mollusks, chordates, even the very first ancestors of you, floating now like a daydream. The arms race is on. Eyes evolve, jaws evolve, armor evolves. The oceans go from squishy and sleepy to bitey and stressed in under 20 million years. And all of it is driven by basic physics: pressure, leverage, vision, flow. That trilobite, its compound eyes are made of calcite, a literal crystal eye. It's using optics to hunt because physics loves a dramatic entrance. Meanwhile, the continents are drifting slowly across Earth's surface. Plate tectonics, remember that from your molten Earth days, is still doing its restless dance. Supercontinents form and break apart. Ocean currents shift. Climate patterns ripple outward. Evolution responds. Fringe alert. Some fringe biologists believe that the Cambrian explosion wasn't an explosion at all, but just a gap in the fossil record. That maybe complex life was around before, we just haven't found its receipts. Others suggest Earth was struck by massive solar flares or high radiation bursts that spiked mutation rates. Physics says, maybe, try again. Above all, it's clear now that evolution isn't a straight line. It's a branching, meandering, occasionally drunken tree. Species appear, dominate, vanish. Some stick around, most don't. You float past entire genera that will never see a future, beautiful failures etched in ancient stone. But one branch, just one, starts developing something curious: a notochord, a stiff rod of tissue that gives its body structure, simple but elegant. And with that, we arrive at the earliest chordates. These are your people now. You drift through schools of Pychia, a tiny worm-like creature swimming through Cambrian currents. It's not much to look at, thin, translucent, maybe a couple inches long. But inside, it's carrying the architectural blueprint for the vertebrate body plan. A flexible body axis, muscles arranged in repeating bands, paired eyes. It's practically humming with potential. And from here, things escalate. Fish appear, with bones even. Some hug the sea floor. Others dart through coral forests that will one day become fossilized time capsules. You pause beside one of them, a jawless, armor-plated fish called ostracoderm. Not exactly glamorous, but physics is on its side. Streamlined body, tail fin optimized for thrust, lateral lines to detect water movement. Biology's beginning to play with engineering now. Historians trace vertebrate evolution through these early aquatic engineers, watching jaws evolve from gill arches, fins migrate toward limbs, and eyes grow forward to face the world head-on. Meanwhile, the land waits, dry, bare, but not for long. Because soon, something is going to crawl out of the sea, and when it does, everything will change. But for now, you float through oceans rich with movement. Life is no longer surviving. It's competing, strategizing, innovating. Physics handed biology a toolkit, and biology has started building empires. You rise from the teeming Cambrian seas and drift toward the shore, though shore is generous. The continents are barren slabs of rock, more gray than green, pocked by volcanoes and lapped by foamy tides. No chirping birds, no rustling trees, just wind and silence. But not for long, because something is watching from the shallows, something slimy and wriggling with just enough stubbornness to say, "You know what? I'm done with gills." We're entering the Silurian and Devonian periods now, roughly 400 million years ago. Life has been doing laps in the ocean for eons, but the land, that's the final frontier. And first, plants claim it. You drift gently above mosses and liverworts clinging to rocks like survivors of a shipwreck. They're small, simple, and utterly committed. These early plants don't have roots or flowers or anything showy. They're basically green felt with ambition, but they photosynthesize, and that changes everything. Oxygen levels rise. Soil begins to form. The land slowly smells less like scorched stone and more like potential. And then come the vascular plants, ferns, horsetails, and ancient tree-like things with names like Archaeopteris. These aren't just plants, they're skyscrapers for insects. Fringe fact time. Some researchers argue that Earth's massive coal beds formed during this time are a result of trees evolving before fungi figured out how to decompose lignin, their tough, woody material. Imagine entire forests dying and piling up untouched, literal carbon time bombs. You float upward through the green canopy of these ancient forests. Above you, dragonflies the size of hawks hum by on wings like stained glass. Below, centipedes and millipedes crawl through damp underbrush as thick as shag carpet. But down by the shore, the real drama unfolds. A fin twitches, a gill flutters, and a creature pulls itself forward. Welcome to Tiktaalik, the OG of awkward landings. It's got fins with bones that are suspiciously limb-like. Elbows, wrists, maybe even proto-fingers. Its flat head turns side to side, and it can prop itself up like a lazy seal. You're watching a fish almost become a land animal. Evolution isn't a clean jump. It's a messy, reluctant crawl. Limbs evolve slowly. Lungs develop from swim bladders. Neck mobility becomes trendy. Eventually, these transitional forms give rise to the first amphibians. And boom, vertebrates are on land. You tag along with one, something like Ichthyostega, lurching across damp ground on stumpy legs. It breathes air, but not gracefully. Its skin must stay moist. It still dreams of water at night, but it's made it. The Earth is no longer a two-realm planet. Now life rules both sea and shore. Mainstream evolutionary biology places this amphibious transition at the heart of tetrapod ancestry. Every walking, crawling, hopping land animal you know today owes its existence to those brave, wheezing pioneers. Historians still debate what drove this move to land: escaping predators, chasing food, drought-fueled desperation, probably all of the above. Biology rarely picks just one motivation. And once life gets a grip on land, it doesn't stop. Amphibians diversify. Then, somewhere down the line, eggs become the next breakthrough. Not soft, jelly-like ones like frogs lay. These are amniotic eggs with shells and self-contained moisture, a spaceship for embryos. Now, creatures can leave the water behind entirely. And here come the reptiles. You float above scaly creatures with stubby legs and sharp teeth, basking on warm rocks. They're faster, tougher, more heat-tolerant. They come in all sizes, some no bigger than your thumb, others that could probably stare down a compact car. But the real showstopper, Dimetrodon. It looks like a dinosaur, but it's not. It's closer to mammals. This sail-backed reptile is a thermal regulation experiment on legs. It struts through swamps, soaking up sunlight with its dramatic fin like a solar panel in search of attention. Fringe speculation. Some paleontologists believe those sail structures may have also been used for display, intimidation, or even sexual signaling. Ancient lizards with fashion sense, basically. Back in the sky, clouds gather. Rain falls in warm sheets, and thunder rolls over forests that are thick, swampy, and buzzing with new ambition. By now, continents are rearranging. Plate tectonics doesn't rest. The supercontinent Pangaea is forming, slowly dragging together all of Earth's land into one massive, awkward roommate situation. And with it comes new climate patterns, shifting coastlines, rising mountains, and, oh yes, mass extinctions. Because physics may be predictable, but Earth's long-term forecast, not so much. The late Devonian extinction rolls in like a slow suffocation. It's not dramatic like an asteroid, more like decades of worsening allergies. Oxygen dips, oceans stagnate, shallow sea ecosystems collapse. Nearly 75% of species vanish, especially the reef builders. You drift through the fatting light of a once vibrant coral forest, now crumbling into sediment. Species go extinct without ever knowing they were competing. Physics, as always, has no opinion. It just enforces the rules. But extinction, oddly enough, clears space. Evolution loves a vacuum. With the old players gone, the stage resets. You rise again, gliding through a thickening atmosphere. Plants are spreading. Insects are booming. Vertebrates are diversifying. And soon, very soon, reptiles are going to try something big. But before we meet the thunder lizards and sky beasts of later chapters, take a moment to appreciate this. A few 100 million years ago, no life dared leave the sea. And now, forests wave in the breeze. Animals sun themselves on rocks. Complex eyes scan the horizon. All because physics allowed it. The pressures, the structures, the thermodynamics. It all conspired, patiently and persistently, to turn slime into something that could look up at the stars and wonder. You're standing now on ancient soil, soaked by rain, beneath ferns taller than houses. And something in the underbrush moves. Evolution's just getting warmed up. You part the ferns like curtains and step into a world humming with heat, humidity, and ambition. Welcome to the Carboniferous period, roughly 300 million years ago, where Earth is a lush, steaming greenhouse. Everything smells like moss, decay, and slow-motion destiny. Towering lycopods, giant, spore-bearing trees, stretch 100 feet high. Ferns crowd the forest floor like shag carpeting, and dragonflies with 2-foot wingspans drift lazily through the sunbeams. Their wings shimmer like stained glass as they cruise over swamps that seem more alive than liquid. You float through this green, breathing world and everything feels turbocharged. Why? Oxygen. Lots of it, more than we have today. Some estimates say atmospheric O2 levels hit 35% compared to today's 21%. Insects love this. Their tracheal system, basically fancy straws for breathing, doesn't scale well in low oxygen, but here, they thrive. You dodge a millipede the size of a sofa and glide past a forest of club mosses that look like alien sentinels. Every square inch teems with arthropods, amphibians, and creatures, slowly testing the waters of terrestrial life. one wobbly foot at a time. But the real legacy of this era, coal. As plants grew, died, and piled up in these anoxic swamps, they didn't decompose completely. Instead, they were buried, compressed, and transformed. Over millions of years, those squishy logs and leafy mats turned into thick layers of coal. The same stuff we'll eventually mine and burn and blame for climate change. Yeah, it started as ferns underfoot. Mainstream geology calls this the Coal Age for a reason. The remains of these ancient forests now lie beneath Pennsylvania, Siberia, Australia, and China. Your barbecue coals, possibly made of 300-million-year-old tree farts. Fringe tidbit. Some researchers hypothesize that the eventual drop in atmospheric oxygen toward the end of this era may have contributed to several minor extinction pulses. High O2 levels are great, until they aren't. Forest fires, for example, would have been terrifyingly frequent and nearly unstoppable. One spark, and whoosh, entire ecosystems lit like kindling. You hover near the edge of a shallow lake, where the real stars of this chapter are emerging. Early reptiles. No gills. No water dependency for reproduction. They've developed the amniotic egg, basically a private spa for embryos. Water on the inside, shell on the outside. Now, for the first time, vertebrates can leave the water entirely and never look back. One of the earliest is Hylonomus, a small lizard-like creature scampering through the underbrush. It's got scales, strong limbs, and it knows how to avoid becoming lunch. It might not look impressive, but its descendants will include crocodiles, birds, and eventually, well, us. Historians trace the rise of the amniotes, the group that includes reptiles, birds, and mammals, to this moment. The egg was the innovation that broke the tether to aquatic environments. It was, in evolutionary terms, a jailbreak. And now that animals are fully land-capable, the planet starts to fill with new designs. Long legs, sharp teeth, sun-soaking scales. Some of these creatures get large. Some stay small. But a few will, over the next 50 million years, become colossally ambitious. You drift forward in time into the Permian period. The forests change. The air dries. Pangaea is now fully assembled, a single landmass stretching from pole to pole. That might sound exciting, but it's bad news for biodiversity. Supercontinents aren't kind. They make harsh interiors, dry climates, long migration paths, massive deserts, and fewer coastlines, which means fewer shallow marine ecosystems. Physics doesn't play favorites, it just applies pressure. But despite the struggle, life adapts. The synapsids, in particular, begin to shine. These are reptiles with some mammal-like features, strong jaws, differentiated teeth, complex skulls. You hover beside Dimetrodon again, basking under a Permian sun with its giant back sail glinting in the heat. Fun twist, Dimetrodon is more closely related to mammals than to modern lizards. That sail, likely for thermoregulation. Think solar panels, not fins. Still, Pangaea's stress is building. Oxygen levels dip, CO2 rises, volcanoes stir, and then boom. You witness the largest mass extinction in Earth's history, the Great Dying. It hits around 252 million years ago at the end of the Permian. Over 90% of marine species vanish. Nearly 70% of land vertebrates. Coral reefs disappear. Forests collapse. Insects take a nosedive. It's full ecological reset. Mainstream science points to massive volcanic activity in what is now Siberia, the Siberian traps, as a major culprit. CO2 and methane flood the atmosphere. Temperatures soar. Ocean acidity spikes. Anoxic events suck the oxygen out of the seas. Fringe theory. Some speculate a nearby gamma-ray burst or methane clathrate explosion triggered the final collapse. But really, it was probably a cocktail of all the worst things happening at once, like if climate change, deforestation, and a volcanic hangover all showed up to the same party. You drift over scorched earth and acidic oceans. The forests are gone. The skis are heavy with ash. It feels like everything is ending. But it's not. Physics doesn't mourn, it recalculates. A few scrappy species hang on, some reptiles, some amphibians, some stubborn little burrowers with lungs tough enough and metabolism slow enough to ride out the storm. And in the clearing silence, evolution stretches its limbs and looks around. The age of the dinosaurs is coming, and they won't just walk the earth. They'll own it. You rise out of the ashen aftermath of the Great Dying, drifting over the charred husks of forests and oceans still reeling from suffocation. The Permian extinction was the cosmic equivalent of pulling the tablecloth off a dinner table and taking half the silverware with it. And yet something stirs. Life is nothing if not opportunistic. You hover over scorched ground as green begins to creep back in. A fern here, a moss patch there. And then in the distance, something new. Reptiles, survivors, architects of a coming empire. It's the dawn of the Mesozoic era, the middle life of Earth's history. First stop, the Triassic period, roughly 250 million years ago. You feel the atmosphere thinning out, the climate warming, and the continents still locked together in Pangaea's awkward embrace. And then you see them. Tiny, upright reptiles darting across the rocks. Some look like lanky lizards, others like awkward crocodiles doing yoga. These are archosaurs, the ancestors of both dinosaurs and modern birds. They're scrappy, fast, and strangely confident, as if they know what's coming. Not far off, early mammals are emerging too. Small, furry, and mostly nocturnal, they keep to themselves. These shrew-like creatures are quietly writing the blueprint for something very big, but they won't get their spotlight for a while. For now, this is a reptile's world. You drift through ancient valleys as the dinosaurs make their entrance, not suddenly, but in stages. First, creatures like Aeoraptor and Herosaurus, small bipedal hunters, scurry through fern fields chasing insects and anything slower than them. Then come the sauropodomorphs, early cousins of the long-necked giants to come. And physics, as always, is behind the scenes, checking its work. Dinosaur legs are set underneath their bodies, not splayed to the sides like in lizards. That little change in biomechanics, huge deal. It makes them faster, stronger, more efficient movers. Gravity, friction, muscle leverage, all optimized. As the Triassic unfolds, climates stabilize, vegetation spreads, and the first true dinosaurs start to dominate. Herbivores get bigger. Carnivores get sharper. By the time the Jurassic rolls in around 200 million years ago, the world is ready for the main event. You fly over forests of towering conifers, ferns the size of houses, and rivers teeming with crocodilian shapes. But it's the sky that captures your attention next. Pterosaurs. No, not dinosaurs, close cousins. They're the first vertebrates to achieve powered flight. You drift alongside a Ramphorhynchus, its leathery wings stretched wide as it dips and rolls through humid thermals, snagging fish with its needle-toothed jaws. And below, dinosaurs have leveled up. Welcome to the Golden Age. Brachiosaurus grazes treetops like a giraffe with a crane's neck. Stegosaurus trundles past, its plate-armored back and walnut-sized brain soaking up sun and suspicion in equal measure. Over by the river, Allosaurus sharpens its hunting skills with toothy precision and a dramatic sense of timing. Mainstream paleontology paints this era as one of unprecedented biological diversity and gigantism. Why were dinosaurs so big? It's still debated, but physics plays a key role. Their efficient lungs, hollow bones, and high metabolic rates allowed for massive body sizes without overheating or collapsing under their own weight. Fringe theory interlude. Some argue Earth's gravity may have been ever so slightly weaker in the past due to planetary expansion or cosmic shifts. No mainstream support, but it's the kind of idea that makes physics students stay up way too late. You hover above the shifting continents. Pangaea is finally breaking apart. Cracks form, oceans seep in, new coastlines emerge. This reshuffling of landmasses shapes not just the geography but the climate, and evolution rides every tectonic ripple. Now you're gliding into the Cretaceous period, the final act of the dinosaur era, roughly 145 to 66 million years ago. By now, the stage is packed. Triceratops, Ankylosaurus, Spinosaurus with its crocodile snout and sail-like back haunts river deltas. And then him. You see Tyrannosaurus Rex before you hear it. It doesn't roar, that's just movie magic, but the sound of its footsteps, deep, deliberate, seismic, is enough to make you want to evolve wings. It's not the biggest predator that's ever lived, but physics has made it one of the most efficient. Bone-crushing jaws, forward-facing eyes, legs made for power, not sprinting. You drift just out of reach, wondering what it would have been like to face this thing without the protection of 66 million years and a really good vantage point. And all the while, flowers are blooming. That's right. While the dinosaurs are stomping and chomping, angiosperms flowering plants are quietly taking over the plant world. They evolve in partnership with insects, offering nectar in exchange for pollination. A deal so effective it rewrites entire ecosystems. Historians of botany often highlight this period as one of coevolution, a dance between plant and pollinator that continues to this day. You, a ghost among petals and beetles, watch it all unfold. Meanwhile, up in the sky, the birds have arrived. Yes, birds, not descended from dinosaurs, they are dinosaurs. You catch sight of Archaeopteryx, fluttering awkwardly between tree branches. It has feathers, teeth, and claws on its wings, a transitional fossil balancing delicately between reptile and avian. Flight, it turns out, wasn't a one-time innovation. It evolved multiple times in different groups: insects, pterosaurs, birds, and eventually bats. Every time, physics did the math: surface area, weight, lift, drag. If the numbers added up, nature gave it a go. And now a shadow passes overhead, a big one. You look up, and your heart, if you had one, would stop. An asteroid. 66 million years ago, a chunk of rock the size of a city is hurtling toward what will one day be the Yucatan Peninsula. You watch it enter the atmosphere. A brief pause, then light. The impact is beyond comprehension. The heat alone sterilizes hundreds of miles. Shockwaves circle the globe. Tsunamis taller than skyscrapers wash inland. Debris clogs the sky, blocking sunlight. Photosynthesis halts. Food chains collapse. Within weeks, the planet plunges into darkness, and then cold, and then silence. It's the end of the Cretaceous, the end of the non-avian dinosaurs, the end of an era. But not the end of the story. Because in the shadows, small, furry creatures, those patient little mammals, are waking up, stretching, sniffing the air. The giants are gone. Time to take their place. Ash still hangs in the sky like a reluctant memory. The dinosaurs, at least the non-feathery ones, are gone. The thunder of giant footsteps is replaced by quiet rustles in the underbrush and tiny, cautious paws. You drift low across a scarred earth where fire gave way to frost and then, slowly, to green again. It's around 65 million years ago. The Cenozoic era has just begun, and mammals, those humble, warm-blooded, mostly nocturnal critters, are about to get their promotion. You spot them in the debris, mouse-sized insectivores with twitching noses and rapidly beating hearts. Survivors. They're the descendants of the small creatures that spent the Mesozoic hiding in shadows, scavenging crumbs from the feet of titans. Now, with the sky cleared and the tyrants gone, they step tentatively into the light. And the physics, it hasn't changed. Thermodynamics still sets the rules. Surface area to volume ratios still determine how fast you lose heat. But now, biology has a little more room to get creative with the tools physics provides. Mammals diversify fast. First come the placentals and marsupials, taking different evolutionary paths depending on where the continents drift. You float over South America as it becomes a laboratory of weirdness, giant terror birds, armadillo tanks, and marsupial lions. In Australia, marsupials go all in, producing an entire zoo of pouch-wearing inventiveness. And then in the north, you catch sight of the early primates. They're tree huggers, literally. Long fingers, forward-facing eyes, gripping toes. They swing from branch to branch with such casual grace it's easy to miss how remarkable it is. Depth perception, fine motor control, brain-to-body ratio. The building blocks of intelligence are right here, lounging in the canopy. Mainstream paleoanthropology dates the earliest true primates to about 55 million years ago. You float near one, something like Archaecephalus, no bigger than your hand, with enormous eyes and a tail that twitches like a nervous thought. And while they may not know it, these little forest creatures are on the road to a very complicated future. But before we jump into primate drama, let's talk climate. The early Cenozoic is a hothouse, literally. CO2 levels are high, temperatures soar, polar regions are lush with ferns and crocodiles. There's no ice anywhere. Ocean currents move differently, shaping weather patterns and biodiversity in every direction. Eventually, plate tectonics comes to shake things up again. Antarctica detaches and drifts south, forming a cold ring around itself. Ocean currents circle the continent like a moody vortex. Temperatures drop. Ice begins to form. And with colder climates comes new selection pressures. Animals get furrier, noses longer. Some migrate, others hibernate. This is the Ice Age in slow motion, a coming attraction that will shape evolution like a sculptor with a sledgehammer. But back to the primates. Somewhere in Africa, about 7 million years ago, two groups split. One takes a path that leads to chimps and bonobos. The other, well, that's you. Not you, just the first in your line. The earliest hominins are still walking upright like they're trying something new and aren't quite sure they like it. Sahelanthropus, Ororin, and later, Australopithecus. You hover beside one now, Lucy perhaps if you time it right. She walks with a waddling stride, upright but still built for climbing. Her brain isn't large. Her tools are sticks and stones, but her hands, the things they'll build. Historians of science love to remind us that walking on two legs wasn't about intelligence, it was about efficiency. Bipedal locomotion uses less energy over distance. It frees the hands, it raises the eyes. From a physics standpoint, it's an optimization, not a revelation. Still, something about it changes everything. Fringe theory detour. There's a hypothesis called the aquatic ape theory, suggesting that early humans went through a semi-aquatic phase, explaining our hairlessness, our ability to hold our breath, and our affinity for swimming. It's widely rejected by mainstream science but still floats around like a wet towel in anthropology forums. Regardless, upright walking evolves, tools become more complex, stones get sharper, hides get scraped, fire gets stolen from lightning and tamed. And with fire comes a massive energy unlock. Cooking food breaks it down faster, making calories more accessible. Brains, which are absurdly expensive organs in terms of energy, suddenly have a budget surplus. You glide beside an early Homo erectus poking at embers, eyes reflecting flames. The air smells of smoke and cooked meat. Their camp is quiet, but it hums with something new: memory, planning, story. By now, you've seen a lot of species. Most rise and fall without fanfare. But this one starts to rewrite the rules. Stone tools give way to hand axes, then spears, then fire-hardened tips. Social groups form. Migration begins. Homo sapiens will show up around 300,000 years ago, but the ancestors are already making their way across Africa, into Asia, into Europe. You float high now, watching campfires spread like constellations across the continents. They fish, they hunt, they bury their dead, and somewhere just barely audible beneath the wind, someone sings. Because while physics wrote the laws and chemistry built the tools, it's biology that's been shaping the characters. And now they're writing back. Language is still a whisper, but it's there. Symbolic thinking, carvings, beads, ochre handprints on cave walls that say, "I was here," across tens of thousands of years. The Ice Age tightens its grip, glaciers creep, megafauna rise, mammoths, saber-toothed cats, woolly rhinos. The cold sculpts the world and humans adapt, clothing, shelters, migration routes. And with every step, every innovation, they bend physics to their will just a little more. From fire to flint, from spear to story, the species born of stardust begins to shape the world in its image. And somewhere, deep in a cave still lit by flickering flame, a child listens to a tale that began long before fire, or stars, or atoms. The story of how physics wrote the universe, and how the universe slowly started listening. You linger in that cave for just a moment longer, tracing the ochre handprint on the wall. It's small, child-sized maybe, but its message is immense. I am here. I existed. I mattered. The air is cool, filled with the scent of smoke and stone. You drift backward through the flickering shadows of firelight and out into the Ice Age night. Humans, modern humans, Homo sapiens, are on the move. They've already spread across Africa, and now they're venturing further into Europe, into Asia, eventually over land bridges into the Americas. They're relentless, curious, tireless, and it's not brute strength that gets them across continents. It's pattern recognition, it's fire, it's cooperation. And beneath all of it, physics, still quietly pulling the strings. You hover above a small band of humans walking across a frozen plain, bundled in furs, moving with the cautious rhythm of survival. Their feet crunch softly over snow. Their tools clink at their belts. They speak in low voices, syllables you wouldn't understand, but intonations that already sound familiar. Urgency, laughter, worry, the rhythm of a species learning to think out loud. Mainstream anthropology marks this as the Upper Paleolithic, a time of rapid innovation. Blades sharpen, clothing becomes tailored, art bursts from the human imagination in 1,000 forms, carved figurines, musical instruments, and the haunting murals of Chauvet and Lascaux. And here's the great trick of physics. While it built galaxies and stars, it also made room for creativity. Energy transforms, structure emerges, and then, improbably, the universe starts drawing mammoths on limestone with charcoal fingers. Let's take a moment to acknowledge just how improbable that is. This is a species made of atoms forged in stellar cores. Their neurons fire using ions. Their speech depends on sound waves traveling through compressed air. Their memories are chemical. Their laughter, pressure from lungs passing through a vibrating windpipe. Physics, again, choreographing every note. And still, there's something more. Something not reducible, perhaps, an emergent property, consciousness, self-awareness, the ability to imagine the future and mourn the past. Historians still debate when exactly this cognitive revolution happened. Was it gradual, sudden, triggered by social pressure, environmental stress, or genetic mutation? No clear consensus, but the evidence is overwhelming. By 40,000 years ago, humans weren't just surviving, they were interpreting. Fringe alert. Some theories propose that early humans may have entered altered states of consciousness through fasting, ritual, or psychoactive plants that helped catalyze symbolic thinking. Whether true or not, it certainly makes you wonder what a shaman saw flickering in the shadows of that first fire-lit story. But back to the bigger picture. You watch as humans invent domestication, not just of animals but themselves. They learn which wolves make better partners, which plants grow stronger when seeds are saved and replanted. Agriculture begins not with tractors and spreadsheets but with baskets and guesswork. Wheat in the Levant, rice in China, maize in Mesoamerica. Slowly, humans start bending ecosystems around their needs. And physics, of course, obliges. You watch irrigation channels etched into the earth, stones shaped into grinding tools, Fire turned into pottery kilns. You float above Göbekli Tepe, an ancient site of massive stone pillars arranged in mysterious ceremonial circles, thousands of years before Stonehenge or the pyramids. Why did they build it? No one knows for sure. Historians argue whether it was a temple, a gathering place, or a giant calendar. But the fact that it exists at all speaks to a shift in priorities. Survival was no longer the only goal. Meaning, ritual, permanence, all were becoming part of the human code. And right beneath those stones, physics, tensile strength, torque, load distribution. The same equations that hold up bridges and skyscrapers today were whispered into place by hands that had never heard the word geometry. You drift through the Holocene now, the most recent 12,000 years of Earth's history. And wow, does the pace pick up. Agriculture leads to surplus. Surplus leads to cities. Cities lead to math, writing, laws, and hierarchies. From Mesopotamia to the Indus Valley, from the Nile to the Andes, human civilization becomes a game of who can solve problems faster. Irrigation, trade, currency, warfare, bureaucracy. You pass over Babylon, where scribes etch cuneiform records into clay tablets. You peek into ancient China as it lays out constellations and predicts eclipses. Over in Egypt, the pyramids are rising, not by aliens, but by organized labor, inclined planes, and a stubborn refusal to let limestone be just a rock. Mainstream historians point to the ancient Greeks as the first to formalize physics into a coherent idea of natural philosophy. Think Aristotle, Archimedes, Pythagoras. They didn't always get it right. Aristotle thought heavier objects fall faster, but they asked the questions that still echo today. And in other parts of the world, knowledge blooms independently. In India, thinkers debate atoms and the nature of motion. In the Islamic Golden Age, scholars preserve and expand on Greek, Persian, and Indian science, developing optics, mechanics, and mathematics centuries ahead of their time. Fringe moment. There's a theory, more poetic than empirical, that human brains evolved not just to understand the universe, but to mirror it. That our minds feel physics because we are physics, highly organized stardust making models of itself. It's a cozy idea. You float with it a moment. Now you're gliding through the classical age. Greek temples cast shadows over sunlit plazas where philosophers argue about the void and the elements. Roman engineers lay aqueducts with an obsessive precision that still holds up today. You hover over Chinese inventors testing kites and seismographs, and Polynesian navigators who chart entire oceans using only stars, waves, and gut instinct. You pause above Stonehenge, noting how its stones align with solstices. You drift through Mayan cities where astronomers chart the sky with unsettling accuracy, calculating celestial cycles without telescopes, using only shadows and patience. All of it, the wheels, the arches, the temples, the sundials, is physics applied without the equations. A world guided by intuition, necessity, and trial and error. And it works, because physics doesn't care whether you understand it. It only cares that you obey it. And humanity, willingly or not, is beginning to listen. You hover now over a turning point so sharp it practically glows, like standing on the edge of a lightning bolt just before it strikes. Humanity has been building pyramids, calculating eclipses, and arguing about the essence of air for thousands of years. But around 500 years ago, something shifts. The questions get sharper, the tools more precise, and the answers, they start fighting back. Welcome to the scientific revolution. It begins quietly enough. A few books, a few telescopes, but soon the entire fabric of how humans think about the world begins to unravel, and then reweave itself in patterns dictated not by tradition or myth, but by experiment. You drift alongside a young man scribbling furiously in the candlelight. His name is Galileo Galilei, and he's about to start a war with the heavens. Using a telescope that magnifies only a little, he looks at the moon and sees craters. not the smooth, perfect sphere described by Aristotle. He looks at Jupiter and sees moons, tiny ones, orbiting not Earth but another planet entirely. And he makes a dangerous suggestion. Maybe Earth isn't the center of everything. Mainstream historians point to this moment as one of the most important in scientific history. Galileo's observations support the heliocentric model proposed by Copernicus, that Earth orbits the Sun, not the other way around. It sounds obvious now, but at the time, heresy, literal heresy. He gets put on trial for it. You hover beside his telescope, watching him make careful notes in ink. He doesn't know it yet, but he's helping humanity step outside of itself. Physics is now being interrogated with purpose, not just guessed at, measured, modeled, graphed. And then comes Newton. You spot him beneath an apple tree, not because of any dramatic fruit-related inspiration, but because he's calculating, always calculating. In his Principia Mathematica, he lays out the laws of motion and universal gravitation. It's not just about falling apples, it's about everything. The moon stays in orbit not because of magic, but because it's constantly falling around Earth in just the right way. Planets move because of forces you can calculate. Newton doesn't just observe the universe, he tames it. He invents calculus to do so. Yes, really. And suddenly, the heavens and Earth operate by the same rules. Historians still debate whether Newton's brilliance was divine inspiration, brutal discipline, or just obsession wrapped in genius. Probably all three. Either way, he gives physics its first real language, math. You ride the ripple effects through the Enlightenment. Scientists, then called natural philosophers, begin testing everything. Torricelli measures atmospheric pressure. Boyle fiddles with gas laws. Huygens explores light as a wave. And through it all, machines are being built. The first steam engines wheeze to life. Thermodynamics is born not from theory, but from trying to pump water out of mines faster. You watch as James Watt improves the steam engine, ushering in the Industrial Revolution. Suddenly, physics isn't just a curiosity, it's profitable. Force becomes horsepower. Heat becomes output. Factories rise, cities swell, and the air starts to fill with soot. Fringe side note. Some alternate historians argue that the scientific revolution could have happened earlier, perhaps in ancient Greece or medieval Islam, if politics, religion, or even luck had allowed. But physics doesn't rush. It waits. Now, electricity enters the stage. You hover beside Michael Faraday as he coils wire around a magnet and notices a current. You drift through Ben Franklin's kite experiment and into the labs of Maxwell, who unifies electricity and magnetism into a single set of elegant equations. Light, it turns out, is just an electromagnetic wave traveling through space at a constant speed. And that speed, it's special. So special, in fact, that it breaks Newton's rules. Cue Einstein. You find him at a desk, not in a lab. He's not holding a test tube or peering into a microscope. He's thinking, deeply, boldly. And in 1905, he publishes 4 papers in 1 year, any one of which could have secured his fame forever. But it's the one on special relativity that tilts the universe sideways. Space and time are not fixed. They bend, stretch, and slow depending on how fast you're moving. The faster you go, the weirder things get. And that little equation, E equals mc2, that's not just a physics flex. It's a revelation. Matter and energy are 2 sides of the same coin. You, the chair you're in, the light around you, it's all energy waiting to be rearranged. You float through the early 20th century as physics fractures into something glorious and bizarre. On one side, general relativity, Einstein's grand theory of gravity. Space-time curves around mass. Black holes form, light bends. On the other side, quantum mechanics, a world so strange that even its discoverers don't quite believe it. You watch Planck quantize energy. You drift beside Bohr as he models the atom like a tiny solar system. And then Heisenberg arrives, uncertainty in hand, and says, "Actually, you can't know both the position and velocity of a particle. Not really." Reality, it turns out, is fuzzy. Historians often call this the most productive, confusing, and existentially destabilizing era in physics. Particles behave like waves. Observation changes outcomes. Cats are alive and dead until you peak. And it's not just theory anymore. You float past the Manhattan Project, where E equals mc2 becomes terrifyingly real. Energy from mass, atomic fire, cities turn to ash. Physics isn't just the study of the universe now, it's the power to rewrite it. But in all this, the quiet genius of Earth is still at play. You drift back down to the planet's surface. Beneath the nuclear tension and the equations scribbled on blackboards, the tides still rise and fall. Mountains still grind against each other. Wind still carves stone. And humans, now armed with the ability to split atoms and measure quarks, still gaze at the stars with the same quiet awe as their ancestors. Because for all the breakthroughs, the math, the machines, the mysteries, we still don't know everything. We're just getting better at asking the questions. And the universe, it's still listening. The lab is quiet and the chalkboard is full. Equations sprawl like climbing ivy, derivatives, integrals, tensors, symmetries. You hover over a physicist's shoulder as they stare at a problem so dense it seems to warp space on its own. Welcome to the quantum age. If Newton's physics felt like clockwork and Einstein's like an elegant fabric, quantum mechanics feels like jazz. It doesn't predict in the way we're used to. It dances, it hints, it flickers. Everything is probabilities now. You shrink down, not metaphorically this time, but truly, and enter the quantum realm. It's not just small here, it's different. Particles exist in superpositions, states that are simultaneously here and there. Electrons don't orbit neatly. They exist in clouds of probability. They're most likely to be in certain regions, but you won't know for sure until you look. And when you look, they chain. You float beside a famous experiment, the double slit. Fire one electron at a time through two narrow openings and it behaves like a wave, interfering with itself. But observe it closely and the interference disappears. It acts like a particle instead. It's as if the universe cares whether you're watching. Mainstream physics embraces this awkwardly. It's weird, but it works. The mathematics of quantum theory powers your phone, your GPS, your Wi-Fi. It explains why the sun shines, why atoms don't collapse, why chemistry is even possible. But it's also unsettling. Fringe alert. Interpretations of quantum mechanics are still a buffet of confusion. Some physicists love the Copenhagen interpretation, where particles only decide what they are when observed. Others lean toward the many worlds interpretation, where every quantum possibility actually happens, splitting the universe into endless copies. You, of course, are floating in all of them. Meanwhile, up at the macro level, Einstein's theory of general relativity continues to hold firm. Planets still orbit. Time still bends around gravity. GPS satellites have to correct for both special and general relativity, or else your food delivery app would drop dinner in the wrong city. The trouble is, relativity and quantum mechanics don't get along. They're both brilliant, but try to use them in the same place, like the singularity at the center of a black hole or the very beginning of the universe, and the math breaks, divides by zero, melts down. Physicists have spent decades trying to unify them. And the latest contenders: string theory, loop quantum gravity, quantum field theory. You drift past these sprawling frameworks, built on elegant assumptions and deeply weird dimensions. String theory, for example, proposes that all particles are just tiny vibrating strings in a 10 or 11-dimensional universe. Why don't we see the extra dimensions? Because they're compactified, curled up like sleeping cats inside every atom. Fringe idea within a fringe idea. Some theorists wonder if black holes are actually portals to other universes. That may be the center of every black hole, far from being a point of infinite density, is a bounce, a gateway, a beginning. But let's not fall in just yet. Back on Earth, physics has found a new lab, the human brain. You drift through neurons firing, synapses blinking like city lights at night. Everything you think, feel, or remember is just the movement of ions across cell membranes, electrical pulses traveling down axons, leaping across tiny chemical gaps. And yet, it's not just electricity. It's thought. You pass through a memory forming in real time. A child learns to ride a bike. A musician finds the right chord. Someone remembers the smell of their grandmother's kitchen. These aren't just impulses. They're the sum of 1 billion invisible calculations, organized in layers we don't fully understand. Mainstream neuroscience is still working on this. We don't know exactly how consciousness emerges. It's not located in one place. It's distributed, dynamic, slippery. And physics, it's in every molecule of it. Thermodynamics governs your metabolism. Electromagnetism pulses through your brain. Quantum effects might even contribute to cognition, though that's highly controversial. Most neuroscientists would rather keep quantum mechanics in the lab, not the cortex. But regardless of the mechanics, the outcome is profound. Because now physics has made a being that can contemplate physics. And you, dear listener, are that being. You think, you wonder, you remember, you ask why. And your asking has changed the planet. You drift forward now through time. Cities grow denser. Science accelerates. In the last 100 years, humans have discovered the Higgs boson, mapped the cosmic microwave background, built particle accelerators that stretch for kilometers and recreate moments after the Big Bang. You pass through the tunnels of the Large Hadron Collider at CERN, where protons smash into one another at near light speed. Inside that chaos, for a brief moment, conditions mimic those from the earliest instants of the universe. Tiny collisions, big questions. Meanwhile, humans have left Earth. Satellites orbit. Probes touch down on comets. Rovers roll across Mars. The Voyager spacecraft, launched in 1977, has now entered interstellar space, carrying with it golden records of music, greetings, and diagrams in case anyone or anything ever finds it. Physics built those ships, and physics is guiding them still. Now slow your drift just a little. Breathe. Stretch out in the gravity of what you've seen. We've gone from atoms to art, from particles to perception. The laws of physics didn't just shape the universe. They gave rise to meaning, to wonder, to lullabies and telescopes and whispered goodnights under starry skies. And as you settle into your bed, eyes heavy, breath slow, remember this. You are stardust that learned to observe itself. You are entropy's lullaby, humming gently through a body held together by borrowed time and brilliant math. So sleep now. The universe will keep unfolding without you tonight, gently, quietly, inevitably. The universe doesn't stop just because you're asleep. It never did. Even as your body rests, heart thudding, chest rising, neurons lighting up with dreams, the equations keep running in the background. Gravity still curves space. Electrons still refuse to share orbitals. The second law of thermodynamics still ticks forward with absolute arrogance. But tonight, as you drift, let's peek at what your species has done with all this knowledge. Because humans didn't stop with fire and flint. Once they realized the rules of physics could be bent, optimized, and even gamed, they started building machines. You're floating now over ancient blacksmiths forging blades with rudimentary metallurgy, heating ore, hammering it, quenching it. Not just trial and error, but unspoken physics. Iron changing crystal structures, heat transferring from coal to steel, molecular bonds weakening, realigning, hardening. These early tools were never primitive. They were just uncalculated physics done with a lot of sweat and very little margin for error. Fast forward, the wheel arrives, not just for moving carts but for transferring force. The lever, the pulley, the inclined plane. These are the simple machines your middle school teacher once tried to explain while making unfortunate pulley jokes. But they're also the foundations of engineering. You drift over ancient Mesopotamia, where irrigation systems channel river water using gravity, slope, and a keen eye. Over Roman aqueducts, where water flows uphill through siphons and over arches calculated by sight and stone. Over catapults, trebuchets, windmills, all early attempts to outsource human muscle to physics itself. By the Renaissance, the machines are getting complicated. Leonardo da Vinci sketches concepts of helicopters, rotating bridges, and self-propelled carts, all centuries ahead of their time. He doesn't build most of them, but the thinking matters. He's not asking, can we make a better cart? He's asking, what is motion? What if wings could lift a man? Mainstream history often credits the Industrial Revolution for ushering in the machine age, and rightly so. But the seeds were planted long before steam engines and coal trains. You hover now beside James Watt's famous improvements to the steam engine. The goal wasn't grandeur, it was efficiency. Condense steam in a separate chamber to save heat. Less waste, more power. It was thermodynamics 101, applied without the benefit of hindsight. It's easy to forget, but heat is motion. Molecules vibrating faster and faster. And when you control that motion, direct it, you get work. You get pistons, wheels, pressure chambers. You get locomotion, and with it, transformation. Fringe moment. Some early inventors thought steam power might one day revive dead tissue. That somewhere in those hiss and wheeze pressure valves was the secret of life itself. Think Frankenstein, but powered by coal. Back in the real world, physics isn't raising the dead, but it is accelerating everything else. You pass through the 19th century like wind through gears. Steamships, telegraphs, electric motors, railroads that slice continents in half and redefine the scale of human ambition. And then electricity. You follow lines of copper wire stretched across rooftops, through forests, beneath cities. Electricity becomes the bloodstream of civilization. Faraday discovers electromagnetic induction. Tesla dreams up alternating current. Edison, more into patents than principles, but he lights the bulb and the headlines. Electricity becomes something almost magical. Flick a switch and the sun appears indoors. Warmth, motion, information, power. But we don't stop there. Because now, the human mind starts to reach beyond even light bulbs and engines. It starts asking questions about information itself. You drift into the 20th century and find yourself watching a strange new machine. It's not made of gears and wheels. It's made of logic gates and vacuum tubes. Welcome to the computer. Early computers, room-sized beasts like ENIAC, operate on ones and zeros. Binary, a switch is either on or off, but inside that simplicity lies incredible complexity. Logic, processing, memory. And again, it's all physics. A wire carries current. A capacitor stores charge. A transistor, arguably the most important invention of the 20th century, acts like a valve for electrons. Billions of these tiny switches now fit on a single microchip. You hover over a silicon wafer being etched with impossibly fine circuits. Electrons don't flow cleanly here. They tunnel. They dance. They obey the probabilistic waltz of quantum mechanics. And just like that, the machine age gives way to the information age. Humans start asking new kinds of questions. Not just how can we move faster, but how can we think faster? Not just how do we build it, but how do we model it? Simulations, algorithms, neural networks, AI. Physics doesn't flinch. It's always been about inputs and outputs, cause and effect. Machines just turn those ideas into tangible feedback loops. And those machines get weird fast. They predict the weather. They sequence genomes. They generate music, diagnose diseases, drive cars. You float beside a robotic arm performing surgery more steadily than any human hand could. You skim over data centers the size of warehouses, cooled by rivers and optimized by algorithmic airflow simulations. You're not in the machine age anymore. You're in the machine inventing age. Now slow down just a little. Look around. Machines are humming. Satellites are blinking. AI systems are writing poetry. Mars rovers are texting home. And humans, they're tired, busy, glued to screens, but still reaching. Still tweaking equations. Still pushing turbines. Still trying to get one more mile, one more decimal point, one more launch window. And here on this edge of exhaustion, we arrive at the truth. Machines don't remove physics. They just make it louder. Every lever amplifies torque. Every transistor distills voltage. Every algorithm sharpens cause and consequence. Physics was never just a force. It was always an invitation, one that said, "Here are the rules. Now go build something extraordinary." And you did. You lean closer now, not to the machines themselves, but to the cracks between them. For centuries, physics felt like a closed system, a neat little toolkit for solving the visible world. Pull a lever, calculate a force, predict the orbit, flip the switch, done. But as the 20th century marches forward, something begins to fracture. The rules are still useful, blisteringly useful, but they no longer agree with each other. Beneath the polish of classical physics lies something strange, uneasy, beautiful. You drift back to that moment we skipped past, the day Newton's clean, clockwork cosmos cracked wide open. It starts with Mercury, not the metal, the planet. Its orbit doesn't behave. It processes wobbles slightly out of step, and Newton's equations can't account for the difference. It's a small inconsistency, just 43 arcseconds per century, but it's enough to give physicists ulcers. Enter Einstein again. In 1915, he publishes his theory of general relativity, and suddenly, gravity isn't a force pulling masses together. It's a curvature of spacetime. Planets follow the curves, like marbles rolling along the grooves of a stretched sheet. Mercury's orbit, perfectly explained. You float now in that conceptual fabric. Every mass dimples the universe around it. The Earth curves space a little. The Sun curves it a lot. A black hole, oh, we'll get there, stretches it to the breaking point. Mainstream physicists still regard general relativity as one of the most precise, elegant theories ever crafted. Its predictions have been tested and confirmed over and over, from light bending around stars during eclipses to the ticking rate of satellites in GPS orbit. But down at the quantum level, relativity crashes. It simply doesn't apply. That's because quantum mechanics plays by very different rules. You're back in the atom now, watching particles that don't really exist in any one place. Instead, they smear across probabilities, interfering with themselves, teleporting, flipping states based on the spin of a sister particle halfway across the galaxy. Enter quantum entanglement. You observe one particle and instantly know something about its partner, even if they're light years apart. Einstein called it spooky action at a distance. He wasn't a fan. But it's real, it's measurable, and it violates every instinct you have about causality and space. Historians of physics still debate whether Einstein was merely cautious or deeply skeptical of quantum theory's implications. He wanted a unified field theory, something that would stitch together the cosmos in one clean equation. He never quite got it. No one has. Yet. You hover now in a kind of limbo, the space between theories. The standard model of particle physics explains the subatomic world beautifully, but leaves out gravity. General relativity explains gravity, but breaks at quantum scales. The two most successful theories in physics are like siblings who refuse to speak to each other at Thanksgiving dinner. So physicists keep trying. String theory says maybe everything is made of vibrating strings. Loop quantum gravity tries a different route, suggesting space itself is quantized, made of tiny loops. And every theory brings its own math, its own headaches, its own promise of unification. Fringe moment. Some theorists propose that spacetime itself is an illusion, that it emerges from quantum entanglement, like a hologram generated from relationships rather than locations. In this model, space isn't a stage, it's a product of information. Yeah, it's like trying to meditate inside a Rubik's Cube. Still, these efforts aren't just academic, they touch everything. Black holes, for example, are test cases for unification. At their centers lie singularities, points of infinite density where relativity fails. But their boundaries, the event horizons, give rise to new physics. Hawking radiation, for instance. Stephen Hawking showed that black holes can leak energy, slowly, that they aren't eternal. They evaporate over time due to quantum effects near the event horizon. You float now beside one. Not into it, don't worry, not yet, but close enough to see the space around it warp like heat over asphalt. Time slows, light bends. It's beautiful in a terrifying, this would snap your atomic structure kind of way. And even here at the edge of physics, you feel something almost familiar. Information. Because it turns out, black holes may not erase information, as once feared. They might store it on their surface, encoded in a two-dimensional way. This leads to the holographic principle, a radical idea suggesting that the entire universe might be like a hologram, a 3D experience generated from 2D information. Historians still wrestle with the philosophical weight of this. If true, it doesn't just affect cosmology, it rewrites what it means to be real. You float above this theoretical boundary, blinking at the implications. And while physicists argue over the math, engineers back on Earth are still building more sensitive detectors. Gravitational wave observatories, quantum computers, particle colliders that simulate conditions moments after the Big Bang. The more we break the universe into pieces, the more it seems to whisper, "You're missing the big picture." And perhaps that's the lesson. That the neat divisions we made, between the classical and the quantum, the large and the small, the real and the imaginary, were conveniences, comforts, bookmarks in a physics textbook the universe never actually wrote. Because in reality, it's all one thing, one process, one unfolding. You, the stars, the laptops, the black holes, the penguins, just different arrangements of energy and space, obeying the same rules in different keys. So now, as you ease into deeper stillness, take a long, slow breath and consider this. You're lying in a bed on a planet that is spinning through space, orbiting a star, in a galaxy, in a web of galaxies, stitched together by forces so consistent that we can describe them with equations, but so mysterious we still lose sleep trying to understand them. Your bones obey gravity. Your heartbeat obeys electromagnetism. Your breath obeys thermodynamics. And your thoughts, maybe those too, or maybe not. Either way, physics isn't done. And neither are you. Shrink now, smaller than atoms, smaller than protons, smaller still, until even the nucleus of an atom seems like a stadium in which you're no bigger than a wandering thought. This is the quantum realm, not the sci-fi kind with tiny superheroes and CG cities, but the actual fabric of existence at the smallest meaningful scales. Here, particles aren't particles the way you're used to thinking. They are excitations in fields, ripples in invisible cosmic fabric stretched across all of space. Electrons, ripples in the electron field. Photons, ripples in the electromagnetic field. Even the elusive Higgs boson is just a ripple in the Higgs field, a kind of molasses that gives mass to otherwise weightless entities. You're not floating through space now. You are space, observing its twitching, vibrating quanta. The entire cosmos, galaxies, mountains, lattes, you is just a temporary dance of energy, rearranged by the invisible puppeteer of quantum fields. Welcome to the Standard Model. Mainstream physics considers this the best tested theory of all time. It includes the electromagnetic force, the strong and weak nuclear forces, and the quantum fields that govern every particle we've ever seen, except gravity. Still the odd one out at the party. It's not flashy, it doesn't explain everything, but it's reliable, like a calculator that's seen too much. You hover near a collision in a particle accelerator. Two protons scream toward each other at nearly the speed of light. When they meet, the kinetic energy is so high that matter is briefly stripped of its identity. Quarks and gluons, those cozy subatomic bedfellows, come unglued. New particles blink into existence, only to decay in less than the blink of a blink. Somewhere in this chaos, the Higgs boson makes a brief, glorious appearance. The Higgs field permeates all space like an invisible fog. Most particles glide through it effortlessly, but others, like the W and Z bosons, get bogged down, and that drag is what we experience as mass. It's not that mass is a thing you have, it's a thing that happens to you as you move through the Higgs field. Fringe alert. Some theoretical physicists speculate that the Higgs field may be linked to cosmic inflation, the rapid expansion of the universe in its first fractions of a second. If true, that would mean mass itself is somehow entangled with the beginning of everything. And speaking of beginnings, you're now drifting toward the Planck scale, the limit of what physics can currently describe. It's where our understanding ends and the math starts to scream. Lengths so small they might as well be zero, times so brief they defy causality. Energy so dense that space, time, and quantum uncertainty melt together into a stew of pure potential. We don't know what's there. String theory tries, loop quantum gravity tries, but so far, nature hasn't given up her secrets. You pause on the edge of this mystery. It's quiet, not in the peaceful, forest stream kind of way, but in the unsettling, something huge and unresolved lurks here kind of way. And just like that, you zoom back out. Your atoms realign. Your molecules cohere. You reassemble into something shaped like you. You are composed of quarks and protons, electrons dancing in orbitals, all glued together by fields that obey quantum rules with exacting discipline. And yet you don't feel quantum. Why? Because of decoherence. Quantum systems are delicate. They exist in superpositions, states where multiple outcomes are simultaneously possible. But the moment they interact with the environment, air, light, a sneeze, they collapse into a definite state. Reality chooses a path. This is why your cat isn't both on the bed and in the fridge. Quantum weirdness doesn't scale well. Macroscopic things decohere fast. And that includes you. So even though you're built from particles that do impossible things, you live in a world of classical predictability. Apples fall, bells ring, your coffee cools, you pay taxes. Physics gave you quantum dice, then handed you Newton's instruction manual and said, good luck. But don't feel shortchanged. Without quantum mechanics, atoms wouldn't exist. Electrons would spiral into nuclei. Chemistry would collapse. There would be no stars, no sunlight, no you. So maybe it's good that you only occasionally glitch into quantum weirdness. Yet you can exploit it. Quantum tunneling, for instance, lets particles slip through barriers they have no business passing. In your world, that's used in flash memory, fusion reactors, and the inner workings of the sun. And now, quantum computing. Theoretical for decades and now inching toward viability. These machines don't use bits, they use qubits, and qubits can exist in multiple states at once. Imagine doing every possible calculation in parallel. Sounds like magic. It's not. It's just quantum mechanics dressed in a lab coat. Of course, they're finicky, sensitive to noise, temperature, the wrong stare. Building a useful, stable quantum computer is like trying to juggle soap bubbles during a thunderstorm. But progress is being made. You drift beside a quantum lab now. The cooling systems hum. Superconducting circuits pulse. Entanglement hums like background music only the particles can hear. And somewhere in this quantum latticework, a problem is being solved that no classical computer could touch: molecular modeling, cryptography, optimization problems with thousands of tangled variables. The future belongs to those who can think like particles. Fringe moment. Some speculate that consciousness might arise from quantum processes in microtubules inside neurons. The Orchor theory, proposed by Roger Penrose and Stuart Hameroff, is controversial but tantalizing, a whisper that your thoughts might not be entirely classical after all. You're not convinced, but you're curious, and that curiosity is quantum. It's a superposition of not knowing and wanting to know. It collapses only when you observe, when you test, when you learn. Back at the particle level, the standard model works beautifully, but it's incomplete. It doesn't include gravity. It doesn't explain dark matter. It doesn't tell us why particles have the masses they do. And it doesn't account for dark energy, that mysterious force pushing the universe apart faster and faster. You're left with a paradox. Physics has uncovered the most precise, powerful descriptions of nature ever devised. And yet, the biggest questions remain unanswered. What is space-time really? What happened before the Big Bang? What is consciousness? Why is there something rather than nothing? And maybe most haunting of all, is the universe deterministic or not? Is the future written or merely probable? You float in the silence of this uncertainty, and for once physics says, we don't know. But the formulas are still running, the particles still dance, and in the space between certainty and curiosity, something beautiful emerges. Not answers, but wonder. Now widen your gaze. You've spent enough time buried in quarks and equations. Let's zoom out, far out, galaxies out. You're floating past the Milky Way now, watching it spiral lazily in the vast velvet of space. 100 billion stars, each one a sun, many with planets. It drifts like a pinwheel caught in a cosmic current, quietly obeying laws written 13.8 billion years ago. And all around you more galaxies, tens of billions, each full of stars, gas, dust, hope. And yet, they're moving away from you, all of them, in every direction. You're not that repulsive. It's just the universe expanding. Not like an explosion, mind you. It's not that galaxies are flying away through space. It's that space itself is stretching. The distance between everything is increasing, even as everything stays still. Like ink dots on an inflating balloon, galaxies recede from each other not because they're moving, but because the balloon is growing. This is Hubble's legacy. Edwin Hubble in the 1920s looked at the light from distant galaxies and noticed something odd. It was redshifted. That means the light waves were stretched, shifted toward the red end of the spectrum. The farther the galaxy, the redder the light. Space was expanding. Mainstream cosmology builds on this. The farther you look, the faster things seem to be moving away. The expansion isn't linear, it's exponential. And here's the kicker, it's accelerating. Why? We don't know, so we gave it a name, dark energy. Dark energy makes up about 68% of the universe. Dark matter, another 27%. That means the stuff we can actually see, stars, planets, you, toaster ovens, makes up only about 5% of all that exists. You float now in this 95% mystery. It's cold, it's vast, it's strangely quiet. Dark matter, invisible and inert, holds galaxies together with its gravitational pull. We don't know what it is, but we can see what it does. Stars and galaxies orbit far too quickly to be explained by visible matter alone. Something else is pulling, something dark. Fringe hypothesis. Some theorists suggest modifying gravity itself. Maybe our equations are just slightly off at large scales. Others think dark matter could be exotic particles, WIMPs, axions, or even primordial black holes. It's a cosmic whodunit with no clear culprit. But dark energy is even weirder. In 1998, two teams of astronomers observed distant supernovae and found that they were dimmer than expected, meaning farther away. This suggested the universe's expansion wasn't slowing down from gravity as expected, but speeding up, as if the universe drank a Red Bull and decided it was late for something. So what is dark energy? A force, a field, a property of space itself. Historians still argue whether Einstein accidentally predicted it back in 1917, when he added the cosmological constant to his equations to keep the universe static, a tweak he later called his greatest blunder. But maybe it was. Maybe space has an energy of its own, a push, a slow, persistent breath outward. You hover now near a galaxy cluster, not a single galaxy, hundreds all caught in a slow gravitational ballet. Between them, dark matter forms invisible webs. Around them, dark energy pushes gently, stretching the universe like taffy on a cosmic scale. And through all this, the cosmic microwave background still hums quietly, like an ancient lullaby. That faint radiation, 380,000 years old, holds tiny irregularities, ripples from the infant universe, that seeded every structure we see today. You realize something. The universe is not just expanding, it's aging. The stars are getting older. The galaxies are spreading thinner. The night sky is dimming, one imperceptible tick at a time. You float beside a spiral galaxy, one among billions. It spins beautifully, held together by gravity and dark matter. Its arms gleam with young stars, but its core pulses with an old, tired glow. Eventually, star formation will slow, gas clouds will run out, the stars will grow redder, cooler. The universe is entering middle age, no crisis, just entropy. You remember the second law of thermodynamics. Entropy increases, always. Energy flows from order to disorder, heat disperses, systems decay. And as galaxies drift apart, the background temperature of the universe keeps falling. It's about 2.7 Kelvin now, just above absolute zero. In trillions of years, it will dip even closer to zero. Cold, empty, dark. That's what the Big Bang leads to. Not a bang, but a long exhale. Fringe moment. Some cosmologists propose alternatives to this ever-stretching fate. Maybe the universe will collapse again in a big crunch, or bounce into a new cycle, or maybe we live in a multiverse, a single bubble among infinite others, each with its own physics. You drift at the edge of such speculation. Theories branch like coral in the dark, some elegant, some speculative, some just math doodles with cosmic ambition. But whether the universe expands forever or folds back on itself, there's a strange comfort in knowing that it moves, that it evolves. Because physics isn't about stillness, it's about change, about rules that hold even as everything reshapes. Now tilt your view again. Zoom back toward Earth, that fragile blue dot orbiting one mediocre star in the quiet corner of one galaxy. A planet full of noise, invention, confusion, and curiosity. Physicists here are still chasing dark matter, still refining particle detectors buried deep in mountains, still launching telescopes that peer further and further into the past, still asking. You land gently on the rooftop of an observatory. A lone researcher gazes at the sky, not looking for answers exactly, but for clues. A flicker of light, a shift in red, a ripple in the gravitational web. The data pours in, the math sharpens, and still the mystery deepens. Maybe we'll never find out what dark energy is. Or maybe one night someone will look up at the stars and say, "Of course." And the universe, as always, will nod in silence. You drift now toward gravity's final stage, the most dramatic, the most incomprehensible, and frankly, the rudest. It doesn't come with fanfare. No explosion, no warning, just a quiet point of no return. A black hole. You float at its event horizon, the edge of forever, the threshold beyond which not even light escapes. No glowing border, No "here be dragons" sign, just space, warped so intensely that direction stops making sense. You can't go back, you can only go in. But don't worry, you're an observer, not a participant. You'll survive, kind of. Let's talk physics. A black hole isn't a thing exactly. It's a region, a solution to Einstein's equations where spacetime folds in on itself. You can make one by compressing enough mass into a small enough space. For Earth, the size would be a marble. For the Sun, about 6 kilometers wide. When stars more massive than about 20 suns reach the end of their lives, their cores collapse. Supernova. Boom. The outer layers explode, the core implodes, and spacetime wrinkles like a shirt caught in a blender. A singularity forms, an infinitely dense point where the known laws of physics flatline. Mainstream physicists hate singularities. They're where our math fails and our metaphors collapse. We can describe everything up to that point, but beyond it, silence. And surrounding that singularity is the event horizon, the no-go zone. Not a physical surface, just a boundary where escape velocity exceeds the speed of light. Cross it, and the universe no longer considers you part of the story. You float just outside, time beginning to stretch. From your perspective, anything falling in slows, reddens, and eventually freezes at the edge, forever caught in slow motion. But from the falling object's perspective, it plunges inward, past the point of return, toward the singularity in mere seconds. It's all about reference frames. Relativity loves those. Black holes don't just swallow matter, they affect everything. Their gravity bends light into spirals. Their presence drags spacetime along with them, a phenomenon called frame dragging. If a black hole spins fast enough, and they often do, it can twist nearby space like a spoon in honey. And they're not rare. Our galaxy has millions. At its very center lies a supermassive black hole, Sagittarius, 1,000,000 times the mass of our Sun. It's mostly quiet now, but once it likely devoured stars like popcorn. Fringe alert. Some scientists speculate that black holes could be gateways, wormholes maybe, bridges to other parts of the universe, or even seeds for entirely new universes budding off from ours in isolated bursts of spacetime origami. No evidence yet, but physics can't help wondering. You loop around the black hole now, skimming its accretion disk, a ring of matter spiraling inward at nearly the speed of light. It glows brilliantly, hot enough to outshine entire galaxies. Friction, compression, radiation, all dancing on the edge of annihilation. This is where black holes stop being silent. They're loud. X-rays scream out. Jets of particles blast perpendicular to the disk, ejected at near light speed by magnetic fields so intense they make MRI machines look like fridge magnets. You hover beside one of these jets, watching it extend for light years, threading intergalactic space with power and chaos. It's both beautiful and uninviting, like a campfire on a planet that's actively exploding. Then silence. The black hole consumes too much. It spins down, the disk thins, the jets stop. And the black hole waits. They don't die easily, but they do evaporate, slowly. Stephen Hawking predicted this in the 1970s. Quantum effects near the event horizon allow black holes to emit radiation, not because anything escapes, but because particle-antiparticle pairs near the edge behave strangely. One falls in, the other escapes. Over time, trillions upon trillions of years, a black hole loses mass, shrinks, fades, until one day it vanishes in a final whisper of Hawking radiation. Mainstream physics accepts this, but with a caveat. What happens to the information? According to quantum mechanics, information can't be destroyed. But when a black hole eats something, matter, energy, the Sunday paper, where does the information go? Is it preserved in the radiation, stored on the event horizon, lost forever? This is the black hole information paradox, and physicists are still arguing over it like kids fighting over the last piece of cake. Some propose holographic principles. Others suggest the universe is more fundamentally about information than about matter. Fringe moment. There's a theory that the universe is a black hole, that all of spacetime exists inside a giant cosmic singularity, and what we perceive as expansion is just our side of the event horizon. Again, speculative. Again, fun to think about at 2 a.m. But let's step back from the abyss for a moment. Black holes aren't just monsters, they're editors. They shape galaxies, regulate star formation, drive cosmic evolution. Without them, the large-scale structure of the universe would be a chaotic mess. Gravity alone isn't enough. Black holes bring order through destruction, which, when you think about it, is very on brand for physics. Because what is entropy, if not the universe's way of reshuffling the deck? And yet, you've probably noticed something by now. The more we understand, the more mysterious everything becomes. We went from Newton's clockwork cosmos to a quantum soup of uncertainty, from simple gravitation to rippling spacetime, from particles to fields to information. And now here we are, staring into a gravitational hole in reality, wondering whether it's the end of physics or just the beginning of something new. You float away, leaving the black hole behind. It sits like a period at the end of a sentence that was never meant to be finished. Space is quiet again, but not empty. Galaxies still drift, light still travels, and every once in a while, two black holes collide. When they do, they send ripples through spacetime itself, gravitational waves. These were predicted by Einstein, but first detected in 2015 by LIGO, using laser interferometers sensitive enough to detect distortions smaller than a proton. You watch as two black holes spiral toward one another, dancing a death spiral that ends in a flashless merger. The gravitational waves race outward at the speed of light, distorting space as they pass, stretching and squeezing, ringing like the deepest bell the cosmos has ever struck. You are watching the universe move. Not light, not sound, not matter, but space itself. The music of physics played in the key of mass. And it's still playing. You glide now in silence, not because there's nothing left, but because what's left feels inevitable. Like the moment after the last note of a symphony, when the air still vibrates, and no one wants to be the first to breathe. The universe is still expanding, still cooling, still humming with radiation from its own childhood, but its energy is thinning out like butter spread across too much bread. So you ask the question, how does it end? Not just your story, the story. Physics doesn't shy away from this question. It has models, charts, equations, and multiple terrifyingly poetic scenarios. The most likely one, the Big Freeze. You float toward the distant future, past stars dimming one by one. The galaxies spread further apart, dragged by dark energy into ever-growing loneliness. From Earth, you'd see less and less of the cosmos every billion years, until eventually nothing. No other galaxies, no background radiation, just darkness. Entropy wins. Stars burn out. New ones stop forming. What remains are white dwarfs, neutron stars, and black holes. Even these decay, a universe of embers and then ashes. You drift through this future, past stars that no longer shine, past rogue planets untethered from solar systems, past the gravitational ghosts of a cosmos once full of light. Time continues, but meaning, as you once understood it, evaporates. In 100 trillion years, the last star dies. In 1040 years, yes, that's a 1 with 40 zeros, the last black hole fizzles into nothing via Hawking radiation. After that, just particles, maybe, maybe not. Welcome to the heat death. A state of maximum entropy, no gradients, no potential, no work, no thought. The universe still exists, but only in the most technical, lifeless sense. Nothing new will ever happen again. You can't even call it cold anymore. Temperature is meaningless without fluctuation, without contrast. Everything is everything. Equilibrium becomes indistinguishable from non-existence. But hey, maybe that's not the end. Another scenario, the Big Rip. In this version, dark energy doesn't just keep expanding space, it accelerates, becoming more intense over time. At some point, it overwhelms every force. First, galaxies are torn from each other, then solar systems, then planets from stars. Eventually, atoms themselves are ripped apart, protons, neutrons gone. Space itself unravels. The universe ends not with a whisper, but a scream so silent no one can hear it. Physicists don't love this idea. The data doesn't currently support it, but it's not off the table. Fringe alert, there's a newer niche proposal called the Big Bounce. In it, the universe doesn't end, it restarts, collapses in on itself, then explodes outward again in a new Big Bang. Maybe this has happened before. Maybe it will happen again. In that version, we're just one verse in a cosmic poem with infinite stanzas. There's a comforting symmetry in that thought. Destruction begets creation, ends loop back into beginnings. But the evidence is thin, beautiful but thin. So you float through all these possible endings, frozen, torn, bounced, and wonder, not which one is true, but what they all have in common. And here it is, in every version, physics doesn't stop, it doesn't flinch. The laws continue, energy transforms, entropy increases, equations hold. It's not a matter of endings, it's just continuation until the canvas itself fades. But let's return briefly to a more human scale, the one you occupy now, the one where stars still shine and atoms still sing and time still means something. Because here, in this moment, the end hasn't happened. The universe is still becoming. Somewhere a new star is forming, gas collapsing, fusion beginning, light erupting from the void. Somewhere else, a neutron star spins 700 times per second, broadcasting pulses like a lighthouse on fast forward. And on Earth, a single planet, blue and twitching with life. A scientist sips cold coffee, staring at equations that whisper about the curvature of space. A child looks through a telescope and asks, "What are we made of?" A satellite beams images of distant galaxies, showing light from a time before the dinosaurs even existed. Physics hasn't stopped writing, the ink just dries slowly. In this chapter of the universe, you exist. That's not poetry, it's probability, multiplied by time, stirred by gravity, shaped by fusion, and whispered into reality by molecular chemistry. And the fact that you can ask how it all ends, that's not physics, that's emergence. From all the lifeless rules, momentum, spin, entropy, you emerged, a system complex enough to generate awareness, then questions, then longing. Fringe thought. Some thinkers propose that the universe needed observers, that consciousness is not just a byproduct of matter, but a requirement for it to collapse into reality. The anthropic principle says, the universe must allow beings like you, because otherwise you wouldn't be here to notice it. It's controversial, it leans dangerously close to meaning. But then again, the universe does seem weirdly tuned for complexity, for chemistry, for life. Maybe it's a fluke. Or maybe, in all the timelines and bounces and ripples, this is just one where meaning happens. Where a species on a rocky planet builds radio telescopes, probes the quantum realm, decodes starlight, and then turns all of it into stories, into theories, into bedtime thoughts for restless thinkers. You're almost at the edge now. The edge not of the universe, but of understanding, of language. The math is still running, but it's whispering now. Concepts blur, time softens, motion slows. And still something stirs, not outside the universe, inside you. A desire to know more, to stretch one thought further, to see how it ends. But maybe it doesn't end. Maybe it just fades beautifully into questions we're not quite ready to answer. You return now to the world of the warm and breathing, a quiet re-entry into the skin and structure you left behind somewhere between the atom and the infinite. The room you rest in, the thoughts in your mind, the gentle swell of your breath. They're all part of the same grand story, the same physical rules that govern black holes, spiral galaxies, and fusion in distant suns. This is the final moment, not the end of the universe, just the soft landing of a long, slow dive into everything. So let's turn now, not outward, but inward, to the question you probably didn't realize you've been asking since we started. Why does any of this matter to you? Physics, after all, seems cold at first glance. Equations, units, constants, acceleration, pressure, Planck's constant. It doesn't care about your feelings. It doesn't know what Wednesdays are. And yet, every single experience you've ever had, every choice, every emotion, every memory, is mediated by the laws we've just unraveled together. Let's take your body. You are a bag of atoms wrapped in electromagnetic fields. Your brain runs on electric signals, ionic gradients, synaptic timing. Your bones are calcium crystals that resist compression. Your skin is a pressure sensor network. Your heartbeat, a hydraulic pump governed by fluid dynamics. When you cry, it's physics. When you sing, it's vibrations through air. When you fall in love, a cascade of electrochemical reactions, sure, but all of them obeying thermodynamics, quantum mechanics, and the Standard Model. The very fact that these laws can be written down, that the same math describing the motion of galaxies can also describe the arc of a basketball or the path of your finger across a touchscreen, is astounding. Mainstream science sees no boundary between the personal and the physical. Your sorrow, your laughter, your epiphanies, they're part of the same reality that governs neutron stars. You are not outside of physics. You are physics. And here, where it gets even stranger. You're made of stardust, yes, but not just any stardust. You're made of carbon formed in the core of a red giant, of iron cast in a supernova, of water molecules that have likely passed through volcanoes, glaciers, and the lungs of ancient creatures. The atoms in your hand are billions of years old. Some may have come from a galaxy that no longer exists. They've seen things your consciousness can't even imagine. Historians of science often point out how long it took for humans to realize they weren't at the center of the cosmos. Copernicus, Galileo, Darwin, Hubble, all slowly peeled back the illusion of centrality. But what they revealed was not meaninglessness. It was connection. You are not the center, but you are a node in a vast, ongoing process. You are the universe folded into complexity, into curiosity, and now into awareness. Fringe moment. There's a growing movement among physicists and philosophers exploring panpsychism, the idea that consciousness, or something like it, might be a fundamental aspect of the universe. Not that rocks are sentient, but that awareness might not be an emergent property of matter, but a property of matter. It's not mainstream, not yet, but the fact that it's even considered says something about how much we still don't understand. You drift now through familiar places, the earth blue and vibrant, turning gently in the dark, the moon still watching, the sun still burning hydrogen into helium, still powering weather, photosynthesis, and long Sunday walks. Everything you see, everything you are, still operates under the rules we've explored. And those rules, they're universal, immutable, fair. Gravity doesn't care how rich you are. Entropy doesn't pause for your birthday. Light moves at the same speed for kings and ants. But there's freedom in that. Because within those constraints, life improvises, emerges, evolves, learns. You learned. You learned to walk upright, thanks to torque, balance, and bone geometry. You learned to speak, thanks to acoustic waves, vocal resonance, and breath control. You learned to read, to calculate, to wonder, thanks to neurons firing in patterns that, yes, obey physics, but somehow exceed it. Because from physics comes chemistry. From chemistry comes biology. From biology comes mind. And from mind comes meaning. This is the twist in the tale. The universe may be indifferent, but you are not. You choose, you care, you make things. Paintings, equations, lullabies, engines, playlists, paper, airplanes. You create order in the face of entropy. And maybe that's the real legacy of physics. Not the rules, but the realization that within the rules, you are free. To explore, to understand, to build cathedrals out of stardust and heartbreak. So as this journey comes to its final pause, take one last breath. Feel the gravity pull you gently toward the mattress. Hear the soft rush of air between your nostrils. Notice the electricity firing through a trillion synapses in your skull. That's physics, and it's beautiful.